A girl delivering newspapers travels 3 blocks west, 4 blocks north, and 6 blocks east. And then it says, what is her resulting displacement and her distance? Which part was your question over? A. Part A. So did you draw a picture for it? Okay. So I'm just going to write down number 22. And so our picture, she starts out going 3 blocks west. So there's 3 blocks west, 4 blocks north, and then 6 blocks east. So something like that. So her resultant looks like this. So this is 3 and this is 4. Does that make sense? It's not drawn very well to scale. I apologize for that. But then from that, we can find the resultant. The hypotenuse is going to be 5. Is that part okay? Was it the angle that you had a question about? Okay. So the angle, I've said this to many of you throughout this process, but I want to make sure that this really makes sense. 2 things. When you're adding vectors, you always want to add them head to tail. So I'm going to start here, and my first vector goes over. My next one's going to come right from that one, up and over. And the angle that I'm going to measure needs to always come from where I started. So I started at the origin. That's the angle I'm going to look at. Okay? And so then I would recommend using this side here, and that's the what side of that triangle? Opposite. And then I'm going to use this side over here, and that's the adjacent. So then I look at my purple sheet, or I know from my head that opposite and adjacent, which trig function do I want then? Tangent. Is that okay? So tangent inverse of 3 over 4 should give us our angle. Is that okay? Okay. Is everybody okay with that? Yeah.
So why don't we add the 2 3s and connect it to the other end?
So when we put this all together, we did, right? Like, so there are lots of different ways that, does this person have a name? A girl. That the girl could have gone. So she could have gone 3, 4, 6. Or she could have gone 4, 3. Or she could have gone 5. Does that make sense? Or she could have gone in big circles and whatever. But somehow she gets from here to here. So I want to know the straight line distance. When I'm trying to find the angle, I always want a right triangle.
Okay.
I want a right triangle because that makes my life easy, because I know right triangles. Is that okay?
Yeah.
So that's why I want those 2. Does that answer your question? Are you sure?
A little bit, yeah.
Do you want to ask the question again so that I understand it better if I didn't answer it?
What about with the blocks?
Like how to, so the units will just be in blocks as opposed to in meters.
Well, I mean, do you find it the same way
Yes.
with those values?
Yes. So the label blocks could just as easily be kilometers or meters or whatever.
I mean, I drew my triangle like this.
Oh, I see. But you want to do it from where she started.
Okay.
Because you put it from over here, and she didn't start here, she started over here.
Okay, that makes sense.
Is that better?
Yeah.
Okay, sorry. Other questions, either on that one or other homework? Sean, what you got?
Number 6.
Number 6. Number 6, we've got a vector of 3 and a vector of 4. And then we've got some weird stuff that happens. Which ones did you want to look at? All of it?
C.
C.
C
And D?
Yeah.
Okay. We're going to look at number 6, C, and D. So take a look over here, friends. Number 6. So we've got 2 vectors. A is 3 units in length and points in the positive x direction. So there is vector A. Vector B is 4 units in length and points along the negative y-axis. So that's going to be like this. There's B. So in part C, it says A plus 2B. What does the 2 mean? What does that, any like gut feeling? What is that 2 going to mean? 2 B's. That's exactly what it means. We're gonna take the value of B and we're gonna make 2 of them. So instead of having 1, we're gonna have 2. So it's gonna be A plus 2b's. That's what multiplication means, isn't it? Right? Do you remember when you were very first learning multiplication? That's what they told you, right? It's just this plus this. That's all it is. And so that's your resultant. So this one's going to be, what was it, 3? And this one would be 8. Does that get you where you need to go? And then for D, in D they throw kind of a funny thing at you. They say it's B minus A. What? What do you think the minus means? What does minus mean? What does it mean if you have a negative 7? What's that? Let's get out the number line. You did this in elementary school, didn't you? There's 0. 1, 2, 3, 4, 5, 6, 7. Where do I find negative 7? The same distance away, just in the other direction, right? Do you remember this? Yeah, do you remember learning negative numbers in elementary school? Maybe you learned it in preschool because you guys are really smart. I don't know. Maybe you knew it before you came out of your mommy, but whatever. At some point you had to learn 1, 2, 3, 4, 5, 6, 7, that negative 7 is here, right? It's the same distance away from 0, just in the what? Opposite direction. It means the same thing when you're talking about vectors. So this is just like B plus negative A. Can I draw something that looks like negative A? Yes, yes I can. What's it going to look like? Say it loud, Melissa.
It's going to go in the negative direction on the
Yeah, it's going to go in the negative direction on the x-axis. How long is it going to be? 3. So you're going to have B. B goes down, right? And then from there, I'm going to go negative 3. And then just find my resultant from that. Is that okay? Yeah.
So, kind of simplify it for my brain.
That's fine.
We're taking the Pythagorean theorem
Yeah.
and just adding in those values.
Boom. You got it. And then you have to find the angles too.
Yeah.
Right, but yeah. Other homework questions?
Yeah, so then the angles would be tan and then plugging in those.
Yes.
Okay.
So this would be the tangent of, so this is 3 and this is 4, right?
Yeah.
Yeah.
So then,
Boom, there you go. You got it. You got it. Anything else? Going once. Yes, ma'am. 27. Take a look. 27 says, a person walks 25 degrees north of east for 3.1 kilometers. How far do they walk north and how far do they walk east? So this is kind of like the problems that we've just been doing. So here's my grid. It says that this person walks 25 degrees north of east. So how do I figure out where that is? Which way am I going to face first? It's one of the two. I'm going to face east and then I'm going to turn north 25 degrees, so something like that. And then they want to know how far do I go north and how far do I go east in order to get there. So we're just breaking it up. Does that make sense? Okay. Does that get you where you need to go? Or do you want me to keep talking? I can, yeah. So it said that they went 3.1 kilometers. So then to find the north part, I'll call that the Y. That is the what of that triangle? The opposite, adjacent, hypotenuse.
opposite.
Opposite, does that make sense? So I know that I'm looking for the opposite. I know the hypotenuse. So which trig function am I going to use? Opposite and hypotenuse is sine. So the sine of 25 is equal to y over the 3.1. Is that okay? And you can say no. That's okay. That's okay. I'm not trying to freak you out or rush you.
Okay.
Oh, hello. It's like, I want to be big today. I'm a big kid, darn it. Does that kind of go? And then, so for the x part, you do the same deal, except you're going to use cosine? Other homework questions? Number 8, sure. I'd rather you ask now than to be like sad and I don't know how to do things. Absolutely. We're looking at number 8. Here it comes. A dog searching for a bone walks 3.5 meters south, then 8.2 meters at an angle of 30 degrees north of east, and finally 15 meters west. It says use graphical techniques. I wouldn't. I would do it the same way we've been doing them all the time. Okay? So this problem is very similar. I'll set it up with you. But this problem is very, very similar to the rodeo clown problem. It's like the same setup. But let's go ahead and go through it quick. So number 8. Silly dog. He's going to start moving 3.5 meters south. And then it says 8.2 meters at an angle of 30 degrees north of east. So I like to put in this dotted line so that I can tell what's going on here. North of east means I'm going to start pointing which way? East. And then I'm going to turn north. Okay? So that's going to be something like, was it 30 degrees? Yeah. Like this, and he's going to go really far. And then finally he goes 15 meters west. I think he's lost. Something like that. While you don't have to get out a ruler and measure things, in order to get an accurate feeling of where he's going to be, you do need to make sure that you draw your vectors kind of to scale so that they're not all the same length. Because if they are all the same length, then he's going to go right back to where he, like he's going to like get close to where he came from. But really, he ends up all the way over here. And so then your resultant's going to go from the very beginning, where he started, to that spot that he ended. Okay. So something like that. So far, so good? And then I think the next thing I would probably do would be to break this thing into an X and Y piece, kind of like we just talked about before. Okay? So that you can figure out how far this is. Because really we want to just look at, whoa, what just happened? It's like humongous. It just really wants to be big today. We really want to look at this triangle. Is that okay? So if you find this piece and this piece, then you know how big this is. So you can figure out this one. And you know how big that is, so you can figure out this one. It is, but if you work through it, I think you can do it.
I'm not sure where to draw my line.
Which lines?
So where the dog starts.
He starts at the origin.
Right in the middle.
Yep.
And
He goes south 3.5 meters. And then he goes 8.2 meters at an angle of 30 degrees north of east. Is that okay? And then he goes 15 meters west. And then the resultant goes from the beginning to the end. The beginning of his story to the end of the story.
I see now. I wasn't sure which lines of which.
Yep. These are problems that you can't, it doesn't work to just look up at my picture. You have to like actually work it through yourself, right? Because otherwise, yeah.
Okay, so what's that one black line in the middle?
This one
Yeah.
is the axis.
Okay, and then the green line on top. So
That's part of the 15 meters that he walked west.
Okay.
Okay, are we okay?
Oh, that's fine, because the line doesn't go all the way through it. That's all I'm confused. Okay, I'm good.
Other questions? Anything else I can answer? Okay. I would like for you to close your textbooks. I would like for you to get out some notes. A new page, because we're going to start a new topic. Chapter 3 is split into 2 very distinct sections. We are finished with section 1. We are ready to move on to section 2. Section 1 is very graphical. We have to draw lots of pictures. Section 2, I mean this in the nicest possible way. A lot of students in the past have regarded as the hardest section of the entire semester. And I'm not saying that as a threat. I'm letting you know that because I need you to stay focused with me. I will tell you that in the last couple of semesters when I've taught this course, I've told my students that, like this has always been regarded as the hard part. Those students that have stayed focused with me, at the end of it are like, why is that the hardest part? It's so easy. Okay? So if you stay with me for the next 45 minutes, life is going to be good. Okay? Yes. I will, yeah, in just 1 second. So what I need you to do is get out a separate paper. We're going to write frog example at the top. That's where we're going to start. Yes. Because I think they found this angle here. So it must have gone like that.
Hey,
You can.
stop. Could me out.
No, it does. It has to match with the angle. So if you found this angle, then your answer should say east of north. Yes. Yes. Okay. Here's the situation. This is where we're going to start. We're going to start with something from chapter 2 that I think you should know how to do. You may need to have your equation sheet out. I would like you to determine for me, if I hold the frog right here, we'll say at 1.3 meters, how long will it take him to fall to the ground? Go. I want you to do that problem right now. I held the frog up at 1.3 meters above the ground. My question is for you, how long will it take him to fall? You are very welcome to work with your partners. Write down some givens. Find an equation. Solve it. Once you've got your givens written down, check with your neighbor and see if they match. Once you've chosen an equation, check with your neighbor and see if it matches with what they want to do. Help each other out.
No, that's not. That's just used for delta x equals VA t plus 1 half a squared plus the initial 0. Oh, yeah.
What are we getting for time? How long does it take for that frog to fall? 0. What? 5.2. Do we agree?
No,
5. Just leave.
You need more sig pixel.
5-0.
5.1.
5.2.
5.51.
So it's going to be t is equal to the square root of 2 times delta x over a, right? Is that right? Yeah? 1/2 a. You can put the 1/2 on the bottom. That's fine. 1/2 in the denominator is the same as 2 in the numerator, right? So 2 times negative 1.3 divided by negative 9.81. I'm going to go with 5/1. That's what I think. Are we okay with that?
Yeah.
Okay. Sean, do you understand why?
366.
How did you get 5/2?
You rounded it differently.
I got 0.5198.
Oh, did you do it in multiple steps?
Yeah.
All right. We don't need to fight then. Okay. Is everybody okay with this?
Yeah.
Okay. So now we need to have a conversation. And Sean, because you are not good at rounding today. All right. Let's see if you have these skills. Now you're just saying your human brain saying. Okay. All right. Take a look up here. I'm going to show you an apparatus that I have. Actually, I'll show you the ball bearings that I have first. Got 2 ball bearings. They're round. That's what a ball bearing is. One of them has a hole in the middle. Okay? That's exciting, right? So that means that their masses are the same or different? Different. If I take them and I drop them, and I release them at the same time, which one's going to hit the ground first?
One with.
Now, Dakota, what'd you say?
The same time.
Why?
Because, like, theoretically, because mass doesn't have any effect on.
Is that what you're thinking? Yeah.
And then
We don't care. We don't care. If I release them from 1.3 meters up, how long are they going to take to fall?
9.81 meters.
That's not the question yet. Okay, listen, friends. I need you to listen. You need to answer the questions that are asked. If I release them from 1.3 meters up, how long will they take to fall?
0.51 seconds.
We just figured it out, right?
Yeah.
Doesn't matter if it's a frog or a ball bearing or whatever. Okay? Anything is going to take 0.51 seconds to fall. Do we agree? Okay, so I'm going to drop them. I've tried this in the past and actually to let them go, but human body is not very good at releases, so it doesn't actually work very well for me to actually like show you because then they don't hit the ground at the same time, and then you're like, wait, physics is broken when it really isn't. So I've got this fancy apparatus here. This is not magic. I want to be very clear about that. It's 2 pieces of metal that are held together because one fits in the other one. Okay, that's all it is. Okay, so it's got a bar that goes across here, and it doesn't have a spring in here, so I can pull this back and I can set it back like that. Does that make sense to everybody? Everybody see that? Okay, and then I can hit this, and I'll show you guys in just a second, and it just goes back like that. Is that okay? Does that freak you out? I'm sorry. I didn't mean to freak you out. It's going to do it a bunch of times, but it's not that. It's not that bad. Right? Okay, so I put it here, like that. Oh, and it goes back. You see that? Okay? So there's really no magic. All that it's doing, this rod is just moving backwards to where it started. Is that okay? Nothing super special and scary about that. Okay, so now here's the issue, my friend. You have to hold this.
Okay.
You have to hold it still. That means that you can't shake or move or flinch. Are you okay with that?
Yeah.
Okay. All right. So he's going to hold this here. Okay. And I've got 2 ball bearings. One of them has a hole and one doesn't, right? We got that? So the deal is that the one with a hole in it, I'm going to stick right here and I'm going to put it on the end there so that, now you have to hold this really flat because if you don't hold it flat, then it's not going to be successful. Got it? Okay. So when I do this and when I flip this, right now there's the rod is going through this ball bearing. Does that make sense? It's holding it up. As soon as I flip the switch, what's going to happen to the ball bearing? It's going to fall. Does that make sense? Because there's nothing holding it up. So just like me holding the frog, there's nothing holding it up, it's going to fall. Right? Life is good. Now, at the same moment, this is the part that's a little more stressful, so don't screw up. Yeah. Okay. There's a little divot here, so I can set the ball right here. Now this one's the one without the hole in it. It's just going to rest right there. Okay? So then when I flip the thing, now what's going to happen to that ball bearing?
It's gonna get knocked off.
It's going to get knocked off. And which way is it? Where's it going to go? Draw with your finger the trajectory of it. Where's it going to go? Right? So it's going to go this way and this way. And you are right in the path of
Sweet.
disaster.
Let me shot, dude.
Is it gonna go that far?
Yeah. Should I try to catch it?
Come on, try.
Should I try to catch it? Just
With your mouth.
with my mouth.
Don't let it go inside. Just keep going.
Okay. So, what I need you to do right now on your paper is to make a commitment. I'm going to call the ball with the hole in it. The ball with the hole in it is ball A. The ball without the hole is ball B. The question that I have for you is when we flip the thing and they're both released at the same time, which one's going to hit the ground first? That's what I want to know. Ball A is the one with the hole that's going to go where? Straight down. And ball B is the one without the hole, and it's going to go in that crazy trajectory that you told me. Okay? Make a prediction. Which one's going to hit the ground first? I want you to just write it down. Make a commitment in graphite. Go.
Committed.
Okay. So if you spin it, that's like really good. Okay. You can even put like your fingers underneath the bottom if you want that. Yeah, sometimes it works better. All right. Have you made a commitment? Yes, you make a commitment? All right. All right. Hey, Auntie, will you be willing to take one for the team here? Yeah, she's like, what? It's not actually going to go that far, but can you stand up there so that you can get the ball when it starts to move that way? And I'm going to have you take a step forward. There you go. Yeah, so hop up so that you can grab it.
Like it's literally on my face. It's gonna hit me.
Safety.
Except it's not. You don't actually need safety goggles. So there you go. Okay, so there's one side. And I'm going to have you just kind of keep an eye on this one so I don't have to chase it. Does that sound okay? It probably won't go very far, but you never know. And you might want to come a little closer because I don't think it's actually going to go that far. All right. So this is the part where Zach has to be quiet because if he's not quiet, then we're not going to have any clue what happened. Because you know that these, well, we've heard it before because Sean dropped one earlier, right? So we know that they're going to make noise when they hit the ground. Okay, so you need to listen carefully and watch carefully. And if you're at the back and you want to come up a little bit so you can see this a little better, you're very welcome to do that too. Are you ready? Are they even? Is it flat? Okay. All right, here we go. 1, 2, 3.
Whack. I was right.
What'd you hear?
Simultaneous.
Same. You want to say it one more time? Hear it one more time? Yes? No?
Yeah.
Sure. Yeah.
One more time. All right, let's do it one more time. Should we do it from the high power one?
Yeah.
Ready for that? She's like, whoa! It's like I'm backing up. It's still not gonna go there. It's okay. But we'll put it back to the other one. Just because you never know, right? Maybe this one just wasn't powerful enough. That's, yeah, as far as it's gonna go. All right, here we go. 1, 2, 3. Did they hit at the same time?
Yeah.
Plus or minus a little bit, you know, plus or minus a little, like, maybe not completely flat. But we get the idea. Does that make sense? Same time. How many of you said that when you were making your commitment? A few people. Maybe you read the book already or something? Uh-huh. If you didn't write that down, let me ask, if you didn't say they were going to both at the same time, which one did you think was going to hit the ground first? Ball A, the one that was just going where? Straight down. And that, I think, makes a lot of sense, doesn't it? Why did you think that ball A was going to hit the ground first?
Because it had the hole in it, and thought it would just go like more air pushed through it, and it just go faster.
But wait, which one was going to hit the, if I drop them at the same time, which one's going to hit the ground first?
I said A.
If I just drop them?
Oh, like
If I just let them go, which one's going to hit the ground first?
they both hit.
Same, right? Okay, so then if I put them on the funny apparatus, then I've got ball A going straight down and ball B going like this. And so it makes sense that ball A should hit first, right? Because how far is it going? Like compared to ball B? Less, right? It's just going down. This one's going like, whoa, way out there, right? Because it made some progress. It made some decent X progress, right? So here's the weird thing. Is that you've got ball A moving in one-dimensional motion. I want to draw this picture. You might want to draw this picture too, just to kind of keep it in your brain. So if we have our funny little apparatus, here it is, and if you feel the need to draw Sean behind it, you can. And we've got ball A over here, right? So ball A is here, and its trajectory went straight down and hit the ground. There's ball A. And then ball B started here And it went, hello, like way over here. And I guess I need to make that ground a little bit longer so that it hits the ground over here. Our brains might say, oh, but ball A didn't go very far, so it didn't take very long. What do ball A and B, even when they're launched in this manner, what do they have in common? That all of their displacement?
That acceleration due to gravity.
They both are being accelerated, right? They're both being accelerated in which direction?
Down.
The down direction. And how do their displacements in the up and down direction compare? Same. Okay? This is the key, is that both objects have the same acceleration. They have the same initial velocity in the y direction, we should say. And so they'll have the same time. The x motion and the y motion are completely independent of one another. Okay? The x motion and the y motion, I'm going to say motion are completely independent. Is that okay? Does that sit okay in your brain? Maybe it's not intuitive, but based on what we've seen, these have the same y motion, different x motions, but they both hit the ground in the y direction at the same time. So this next section is called projectile motion. Ball B underwent projectile motion. So to project just means that it's going in like 2 dimensions. You got it in the y and in the x. Here's the secret. You know how to do this already. We did one-dimensional motion already, right? You know how to do one-dimensional motion. I've graded your tests. I'm almost done. I'll give them back to you next time. When you look at the at one-dimensional motion, you guys get it, I think. But all we're doing is it's like 2 problems in 1. That's it. That's it. You can handle that, right? Yeah. Okay. So I want to try a couple of problems with this, and we're going to use the patented Carbling method for projectile motion problem solving. Okay? I will tell you that the textbook does not use this method, and I find the way that the textbook explains things to be very confusing. So if you want to use it, great, but I would recommend my approach. I think it will help. Okay? This is what you need to know to make your life better. I feel like I'm like on some sort of infomercial that you watch at like 3 in the morning when you can't sleep, right? Like, buy this, 5 easy installments of, you know what I'm saying? Like, that's what I'm feeling like, but I'm not even going to sell it to you. I'll give it to you for free. Wow!
What a deal.
I know, what a deal. Can I have 4? Sure, right? Like, that's what I feel like I'm doing now. So, just for you, just today, or all of next week, I can teach it to you again. It's all good. Here we go. For projectile motion, because you're talking about 2 different dimensions, we're going to do kind of the same thing we did in Chapter 2. Do you remember in Chapter 2 when we had 2 objects and we made 2 lists of givens? It's the same kind of deal. So we're going to have the x direction stuff in one column. Whoa, my goodness, now it just wants to be little. I don't know what the deal is with my computer today. There we go. I'm going to make a list of the x stuff, I'm going to call it, in a column. And then I'm going to make a list of the y stuff in a column. We used to always call displacement delta x, but since we've got x and y now, I often will call them d for displacement, sub x and d sub y. If you like saying just x and y, that's fine, but I always write it this way, and I've tried to quit, and it's just really hard. It's like once you have something ingrained in your brain, it's just hard to stop. So I'm going to say displacement in the x. We also often care about the initial velocity in the x and the acceleration in the x. That's all the x stuff that we care about. Most of the time, for whatever reason on these problems, we don't care about final velocity, so I'm not going to worry about it. Then we're going to do the y stuff. Displacement in the y, velocity in the y, the initial velocity, the acceleration in the y, and the thing that ties it all together is what? Time. Yeah. So I put time generally on my little chart. I put time down here. So what we're going to do when we read a problem is to fill in this chart. Fill in as much of this chart as we can, and then make a plan for how to fill in the rest of it. Okay? I want to start with a problem from your book, but I don't want you to look in your book because it's one of the example problems, and I don't want you to look at how they solved it because I find it confusing. Okay? So I'm going to read it to you, so it's a nice listening practice. Okay? I will tell you what page it's on so that if you want to look at it later, you can, so you don't have to like copy all the problem down. It's on page 101, but I don't want you to turn there right now. Okay? I just want you to listen. So here is the problem as it is written in that part of the book. It says, the Royal Gorge Bridge in Colorado. Has anybody been to the Royal Gorge Bridge in Colorado? One time I had a kid, they were like, I've been there, I was there last summer. I'm like, what? Like, really? I just didn't know if there was anybody. I don't know where it is. It's in Colorado, I guess. It rises 321 meters above the Arkansas River. In Colorado. Suppose that you kick a little rock horizontally off the bridge. The kid that was in here was like, I've been there. He's like, I totally kicked a rock off of the bridge. Like, I don't know if he was just trying to humor me or what, but that's what he said. I did it. I did it. All right. The rock hits the water such that the magnitude of its horizontal displacement is 45 meters. The question says, find the speed at which the rock was kicked. So I'm going to read the problem to you again, now that you kind of have it in your head.
Should we write down givens?
I would encourage you to write down givens. It may be easier to draw yourself a little picture first and write down like things in the picture and then go from there. I'm going to start reading it again right now. Ready? The Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose that you kick a little rock horizontally off the bridge. The rock hits the water such that the magnitude of its horizontal displacement is 45 meters. Find the speed at which the rock was kicked.
So 41 meters?
45. 45. So I want you to try to draw a picture. See how much of that chart you can fill in. Okay? I'm going to draw a picture and then we'll fill in more stuff together too.
You said it was
45, right? 45 meters. Once you think that you've gotten some givens written down, check with your neighbors and see if they match what they have.
the x displacement is 45 meters.
acceleration in x there is none, so it'd be 0. And y acceleration is just 1.
Yeah.
So it'd be
Well, you need to have like roundabouts to kick to that baby.
the baby.
It says that it was kicked horizontally.
So the x.
Wait, from rest. So what if like in air it somehow started to run on air and got x?
And it's a rock, not a little kid.
Oh.
It's gonna make like, damn it,
All right.
stay in my 2 spots.
We'll use it later.
All right, let's fill in some things here. First of all, take a look at my picture up here. See if it matches yours. Does this look about like what you have? No. No?
Yes.
What does yours look like, Jenna? Oh, your water doesn't look like my water? Oh, okay. That's okay. That's artistic license. In general, though, are we okay? The things I would encourage you to have on your picture would be any of the heights and distances that you know. And the other thing that I would ask you to draw, because it will make your life easier going forward, it's like I know what's going to happen. You can see the future. I would draw an initial velocity vector so that you remember that it's going exactly which way in this one. Horizontally. So the initial velocity is horizontal. All right. I would like to fill in as much of this chart as I can. Please raise your hand for me if you can tell me something that you had written down. Go into what you got.
The displacement for x is 45 meters.
It is 45 meters. Nice. Go.
The displacement for y is 321 meters.
I agree with you almost completely. I agree that the magnitude of it is 321, but where is the rock going?
The y. Negative 3.
There you go. Cha-ching. Is everybody okay with that? Do you understand this? It's going downward, so that needs to be a negative 321. Fantastic. All right, I've got 2 things down. What else can you tell me? Go.
For the y, the acceleration should be negative 9.81 meters per second squared.
Got it. So I told you we have to fill in this chart every time we do one of these problems. Here's a hint. This thing right here, almost always, 99% of the time, it's going to be negative 9.81 meters per second squared. So that one's like a free one. It's kind of like when you're playing bingo and you have the free space, right? Free space right there. There's another one that's kind of like a free space for most of the problems, 99% of the time as well. Once that rock is kicked, what's going to happen to it for real, Jake?
Wait, acceleration in x is 0?
Why?
Because it's not like accelerating this way, it's just still falling.
Yeah, it's not going to speed up or slow down in the x direction. Does that make sense? If it was going to speed up, that means that the little rock has a jetpack on it. Right? Like that would be a really fancy rock.
Just kicks it and just.
Right? Like that's not happening. It's not going to slow down, assuming that there's no air resistance, right? We assume in this class always that there is no air resistance. It's not going to slow down because it's not, there's nothing slow, so it's not like, it doesn't have a parachute. Even though if it had a parachute and there was no air, it wouldn't slow down anyway, right? But, so it's no rocket pack, no parachute, so that means the acceleration in the x direction will be? 0. Free space, you got it. Okay, we're getting close. We're not quite there yet. I've got 3 things that I don't have filled in. One of them is the thing I wanted to know. What is the thing I want to know on this chart? The initial velocity. It says find the speed, right, at which the rock was kicked. Which direction is the rock kicked? Horizontally in the x direction. Does that make sense? It's in the x direction, so that's the big thing I want to know. So I'm going to put a question mark there. I don't know what that is. I want to know what it is. Do I know time right now? Did they tell us that? No. Do I know the initial velocity in the y direction? What is it, Mitchell?
0.
Why?
Because it's at rest.
Because it's at rest in the y direction, right? Even though it's been given a kick, that kick is all in the kick it to go down. I don't know. It's 0. Okay. All right. Are we okay with this? Any questions? Okay. We need to find this. Right now, we only know 2 things about the x direction. Hard to solve if you only know 2 things. We've learned that, right? You need 3 to find the 4th. We can find time, though, using the y stuff. Do you remember last chapter that I told you there was going to be one equation that you would get to know very well?
Oh.
Take a look at what's in here. We've got initial velocity, displacement, acceleration, and time. Do you have an equation that has those 4 things in it? Yeah, you do. It's the one that you love. I mean, tomorrow is Valentine's Day, right? If you don't have a Valentine, let this equation be your Valentine.
Deal.
There is nothing wrong with having an equation as your Valentine. I don't have a problem with it. Nobody does. Let's use it. Here we go. Dear equation, I love you. I think you're the coolest. Here we go. Let's use it.
I'm here right all over my walls.
That might be like a weird mental thing. I don't know if we want to go there. Here we go. dy, come on now, equals vyt plus 1/2 ayt squared. Can you solve that for time?
Yes.
Have you done that problem already today?
Yes.
Yes.
Yes, we did it with a frog about 15 minutes ago. Go ahead and do it. Find the time. Once you find the time, you can use that with the x stuff and your Valentine equation in order to solve for the Vx. Did you find a time value? How long did you find? How long did that rock take? 8.09 seconds? That's a long time, huh?
Well, you're at 320 meters up.
It's true.
Right.
That's the same time if you
Yeah, I mean, technically, yes.
or an
That's
apple.
dark, man.
He was
Well, I
talking
mean-
about bicycling.
Let's not go.
Exactly.
All right, how we doing? So once you have that time, then use the x stuff to solve for Vx. So again, once you have the time, 8.09 seconds, use that and the 45 meters that it travels in the x direction to find the velocity. John, you look like you have a question. Are you sure? Okay. Are we getting an answer? What'd you get, Anna? 5.6 meters per second. And then the A stuff goes away.
wish.
Yeah. Before you go, I want you to look at one more problem. Turn to page 102. I want you to look at question number 1. You don't have to finish the question. What I want you to do right now is to fill out the chart, the givens chart, for question number 1 on page 102.
Wait, what are we doing on page?
Question number 1, all you need to do is fill out the givens chart.